Hello guys, this is CodeNCode and this is an tutorial for the problem spanning tree with one fixed degree taken from Codeforces. The problem was taken from div3 challenge and it is rated 2200. So let's start. So the problem is very easy to understand. You are given a graph undirected and unweighted with n vertices and m number of edges, and it is guaranteed that there are no self loop, that is no node is connected to itself, or there are no multiple edges, that is between any two nodes there is at max one edge. So we have to find any spanning tree such that the degree of first node, that is node 1, is equal to d, and d would be given with the input. So n, m and d, n can be as large as 2 into 10 power 5 and number of edges can be at max 2 into 10 power 5. D of course can be greater than equal to 1 and less than n. So given a graph, we have to find a spanning tree in which degree of node 1 is equals to d. So let's take an example to make things clear. So the first example is this. There are 4 nodes and 5 edges. One is connected to 2, 3, and this is the graph you can see. So in this graph, what we are asked to find is that find a spanning tree such that the degree of node 1 is 1. This is d. So if the answer exists, we have to print yes and all the edges in the spanning tree. Otherwise we have to print no. Since in this case the answer is yes, that is why we are printing yes. And since the degree of node 1 is 3 and in the spanning tree we want degree 1, so what we can do, we can actually remove any two edges, any pair of edges from node 1, and that would result in a valid answer. So I've removed these two edges, so the result is this. 1 is connected to 2, 2 is connected to 3, 3 is connected to 4, as you can see here. So this is a spanning tree in which degree of node 1 is equals to 1. Now the question is, can we find the result of this this problem each time like this, just removing the remaining edges? Let's see. So take an example of this. Suppose we have to solve for d is equals to 1. So since there are 3 edges, or degree of node 1 is 3, and we want degree of node 1 to be 1, so what we can do, we can actually remove 2 edges. But the problem is, if you remove any 2 edges, for example I have removed these 2, then the graph becomes disconnected. If the graph is disconnected, then there exists no spanning tree. So for d is equals to 1, there is no solution for this graph. So see, in the previous example what we did, we simply removed 2 edges because we wanted degree to be 1, and there were 3 edges, so we removed 2 edges. But the problem with this graph is that if you remove any 2 edges, even if you remove these 2, this would become disconnected. So the graph becomes disconnected, and this, as we can see, is not an absolute solution. So let's see, first of all, what is the condition which satisfies the existence, which confirms the existence of a solution. So what are the conditions for solution? The first thing is that, what if d is greater than 3? Since the degree of node 1 is actually 3, and if given d is greater than 3, that is 5 or 10, something like that, that is not possible. The solution doesn't exist, because since the degree of node 1 is 3, so in the MST, the degree in the spanning tree, the degree of node 1 can be at max 3, because when you construct a spanning tree, degree of a node may decrease but cannot increase. So degree initially is 3, so the degree of 1 cannot increase. So we cannot find any spanning tree out of this graph such that the degree of node 1 is greater than 3. So d must be less than equals to degree of node 1. So first condition is that d must be less than equals to degree of node 1. Now this is upper limit, because d cannot be greater than degree. So this is upper limit on d. Now the question is, what is lower limit on d? So take this example again, and can we find solution for d is equals to 1? The answer is no again, because for degree of node 1 to be 1, you have to remove two edges, any two edges out of these three. But if we do that, we see that the graph becomes disconnected and hence there is no solution. So of course for d is equals to 1 there is no solution. We know the upper bound for d is equals to 3, but lower bound, to define the lower bound we have to go deeper, because we cannot tell what is the lower bound just looking at this example. So let's take this example. This is node 1 and these are the rest node which we do not need to name. To find the lower limit on D, what we can do, we can actually just remove this node 1 and all of its edges. If you do this, you get a disconnected graph. Now count the total number of connected components. You see there are 1, 2, 3 and 4 number of connected components. So the lower limit on D is equals to 4. Reason? In the spanning tree, node 1 must have degree 4 at least. The reason? Suppose these all were connected just because of node 1. Otherwise these connected components are actually disconnected from each other, right? So if you want to connect all of these in a single connected component, then you need node 1 and at least 4 edges, because there are 4 connected components. So one edge for this connected component, one edge for this, one edge for this, and one edge for this connected component. So if there are 4 number of connected components, then the degree of node 1 need to be at least 4. Otherwise the graph would be disconnected, and if the graph is disconnected, of course spanning tree doesn't exist. So the lower and upper bound for D is this. Lower bound is number of connected component and upper bound is degree of node 1. So D must be greater than equal to number of connected component, and D must be less than equals to degree of node 1. Then only solution exists, otherwise no. So let's code at least this part. So first thing that we need is vector for adjacency list. Since there are at max 2 into 10 power 5 number of nodes, I guess. Yeah, there are at max 2 into 10 power 5 number of nodes. So 2, and then we need visited array. For now only this. We need more things, but I'll be taking them when we need only. So we need N, M, D, A and B. So now A, B, we are reading M number of edges. So in the adjacency list of A, add B, and in the adjacency list of B, add A. So this is adjacency list representation of graph. So in adjacency list of A we have added B, in the adjacency list of B we have added A. Now this is number of connected component, because we need to count the total number of connected component. Now mark node 1 as visited, because when you are counting connected component, then we have to remove node 1. To remove node 1, what you can do, you can actually mark it as visited. If you mark this node as visited and you suppose you start with traversing this connected component, then there is no way you can pass through this, because since this node is connected, so you won't make a DFS call. This node is visited, so you won't make a DFS call from this node to this, because this is already visited. So this way we can actually count the total number of connected component by making DFS call from each of the nodes which are not already visited, starting from node 2. So for starting from node 2, if ith node is not visited, then we would make a DFS call to node I and we would increment connected component count. So dfs node, first thing that we do, we mark the current node as visited, and then in the adjacency list of current node, if, let me do this, if current child is not visited, then simply make a dfs call to that child. This is a simple code just to count the total number of connected component. I have explained all of this in my graph theory lecture series part 1, so you can go and check out that if you have no idea how this works. So now we are counting the total number of connected component, and also we yeah, that's what we are doing. And so if number of connected component, if d is less than number of connected component, or d is greater than degree of node 1, then we would print, simply print no, since there doesn't exist any solution. Otherwise we would print yes, and we will print yes, and then we'll find the solution. We will do that in a moment. For just now, let's test this code, whether this is having any error or not. Most likely I thought we are going to get any error. So let's 4 nodes, let's create a test case in which the answer is no. So 4 nodes, 3 edges. I'm going to, for now, 3 nodes, 2 edges, and I'm going to ask for d5. So one is connected to 2, one is connected to 3. The answer is no, because degree of node 1 in the given graph, degree of node 1 is only 2, while d is 5, which is greater than degree. So that is why the result is no. Let's test for the second test case. That is for second condition, number of connected component, that is d, must be greater than equal to number of connected component. D must be greater than equal to number of connected component. So if we make d less than number of connected component, then answer should be no. So again, 3 nodes, 2 edges, and degree I want is 1. 1 is connected to 2, 1 is connected to 3. If you remove 1, then there are 2 connected components. The answer should be no. Yes. And for a valid test case, 3 nodes, 2 number of edges, and 2 degree. 1 is connected to 2, 1 is connected to 3. The answer exists yes. So at least this part we have covered that we have implemented this thing, that d must be greater than equal to number of connected components, and d must be less than equals to number of degree. So now the second thing is how to find the solution. Now to find the solution, what we are going to do, we are going to create a new graph. For that, what we are going to do, this is node 1 and the rest are other nodes. For that, what we are going to do, we are going to find we are going to create a completely new graph out of this old graph. And for that, what we are going to do, we are going to do a BFS, or we can also do a DFS, doesn't matter. So I'll be solving this using BFS. So I'll be marking this as visited, and from the rest of each connected component, I'll be making a BFS call, and we'll add all of the edges which are necessary to make a spanning tree. And how we are going to do, see, first of all, suppose I made a BFS call to node 2, which was, suppose this, right? So I started from here, and since these 2 nodes are unvisited, so I'll be adding this edge. Suppose this is x, this is y, so this edge 2x must be added into the MST. So in the new graph, since these 2 were unvisited, so these 2 edges would be added. After that, since this was added into Q, I'm running a BFS. So from this node, I added these 2 nodes into the queue, because from this node these two were connected and these two were unvisited. So since I'm adding these two nodes into the queue, which means I need to add these two edges in the new graph. So that is why these two nodes I marked as red. After this was into the queue, so it is connected to this, this and this, but these two are visited. So I won't add this edge again, or I won't add this because there is no need to add this edge. But this was unvisited. Sorry, I would be keeping node 1 as unvisited. So node 1 was unvisited, so I would also add this edge, but I won't add node 1 into the queue, because if I added node 1 into the queue, then node 1 would add all of these edges, all of these nodes into the queue as well. But I don't want that. I don't want to pass through node 1, because I have started BFS into this connected component. I want the BFS to end in this connected component. I don't want to pass through node 1. So now I would not add node 1 into the queue, but I would add this edge into the new graph. So this is part of the new graph. Now work of this node is completed. Now in the queue there was this edge, this node, but this node is connected to this, this and this, but all of these three are visited, so this node would not add anything else. So this is from this connected component, these are the edges which are added into the new graph. Now I would make a BFS call from this connected component, which would add these two edges only. And from this connected component, when I make a BFS call, this would add this edge, this one. So that is why this is marked as red. And when I made a BFS call from this connected component, then all these edges would be added. Now this would make a new graph, and in the new graph these would be the edges. And the specialty of this new graph is that each connected component from node 1, there is a single edge to each connected component. So let's construct this graph first. So I is equals to 2, I less than equals to n, I plus plus. If ith node is not visited, we would make BFS call to that node. But before doing that, it is important that we mark all of the nodes unvisited again. Reason? Because when we were making DFS call to each nodes, then each node is marked visited, so it is important to mark them unvisited again. So each time we are making a call to this BFS, and then the work of this BFS is to add all of the edges which are necessary in the new graph. So there must be a new graph as well. So this is new graph. Again, it also have to be the same size. Now we need a BFS function, BFS in source node, starting from this. So this is node 1, so suppose this was node 2, so I would be making BFS call into this connected component. And when we make BFS call to this connected component, all of the important edges have to be added, or all of the edges which would be part of MST, or basically for each connected component we are actually calculating their own MST or spanning tree. So what we do, we create a queue in which we would store integer. We would mark node 1 as visited and also the source node as visited. Okay. We don't need to mark node 1 as visited. We also need to insert q dot push node source node. And how BFS works? Simple. While queue is not empty, get the current node, which is the front node of queue, and remove this node from queue. Now for each child in the adjacency list of this current node, if the current child is not visited, that means that we have to suppose you started BFS from this point, and in the adjacency list of this node there was this node and this was not visited, so you have to add this edge. So for that, what we would do, since this child is not visited, so which means we have to add there is an edge between current and child, and hence in the new graph this edge have to be there. So in the new graph we would add, in the adjacency list of current we would insert child, and in the adjacency new graph, in the adjacency list of child we would insert current node. So this was the edge, and this edge is now added into the new graph. After that, we would also mark the child as visited. Yes, oh sorry, there are two things that we would do first we would mark it as visited, this is important, and also add this edge. Okay, sorry. So first we inserted this edge into the graph, and we mark this child to be visited, and before inserting into the queue we would check whether this child is 1 or not. If child is not equals to 1, because as I have explained earlier, if the child is 1, that I don't then I would not insert this into the queue. Otherwise what would happen, since this was in queue, then it would add all of the nodes from other connected component as well. That is why I would not add node 1 into the queue. If the child is not equal to 1, then only I would insert child into the queue. I think this should do. I have added the current edge into the new graph. I marked the node as visited and also inserted in queue. So I think, yeah, this is good. After adding spanning tree of each connected component, for this connected component spanning tree was this, for this connected component spanning tree was this, and so on. So after adding each spanning tree into the new graph and after constructing new graph, the time is to print the solution. To print the solution, all you gotta do is simply, if you remember from the previous problem, that is F1, from the same challenge I've explained, I've also made an editorial for that problem. If you remember, for a given graph, how we printed the spanning tree, we simply made a BFS from node 1, and that was all. So that is what we are going to do, but from new BFS. Reason, because we already have a BFS function, and so that is why I'm going to create a new BFS function which is going to print the spanning tree from the new graph. And if you print the spanning tree from the new graph, then the degree of node 1 is going to be D, and then the spanning tree would be valid. But there is a problem for now, and I'll be explaining after I complete this new BFS. Source node, we create a queue, we insert source node into queue, we mark source node as visited. These are the elementary steps. And then while queue is not empty, current node is equals to queue dot front, queue dot pop, because we need to remove that node. Have I removed? Yeah, I have also removed from that BFS as well. So after removing, for each child in the adjacency list of current node, but this time we are using new graph. In the adjacency list of new graph of current node, if this child is not visited, we would mark this child as visited, and we would print this edge because this edge is part of spanning tree of our solution. So current and child, we would also insert this child into the queue, but before that we have to mark every node again unvisited, otherwise this would not work. So I think this does the work. Yeah, let's test it for the very basic test case. For this I can simply copy the test case and then print it. So answer is yes. 1 is connected to 2, 2 is connected to 3, 3 is connected to 4. As we can see, 1 is connected to 2, 2 is connected to 3, 3 is connected to 4. That is the solution. But there is a problem. Now what we did, we actually created this new graph in which the degree of node 1 is equal to the number of connected component, because in the new graph, as you can see, from each connected component there is exactly one edge to node 1. So the degree of node 1 would be equal to number of connected component. What if the degree of what if d is greater than number of connected component? So in this if you print spanning tree for this graph, for this new graph, I am talking about only the red edges, the new graph. If you print spanning tree of this graph starting from node 1, the degree of node 1 would be 4 only. But suppose if d was 5, now what would you do? If d is 5 or more than that, in valid range, I'm talking about when d is in valid range, but d is greater than number of connected component. For this case, d is 5, number of connected component were 4 and d is 5. What we are going to do? For that, we must increase the number of degree of node 1. For that, we have to add the extra edges that we have not added yet. For that, I would be traversing all of the first of all you need to count the total number of edges we still need to add. So basically the remaining, so in remaining number of edges are d minus connected component, because we need degree of node 1 to be d, and till now the degree of node 1 is this, so we still need to add these many number of edges. So degree of node 1 is currently cc, that is number of connected component, and total we want d, so we have to add these many number of edges extra. So if d was 5, then 5 if d was 5, then for this example 5 minus 4 is equals to 1, that is we have to add one extra edge. For that, what we would do, we would traverse adjacency list of node 1 and see whether this edge has been added into the new graph or not. For example, this edge, yes, this edge is added, so we can't add this edge is also added, this edge is also added, but this edge is not added. So what we would do, we would also add this edge into the new graph. To know which edge from node 1 is added or not, all we are going to do is we are going to keep a set of nodes to which node 1 is already connected. So I'm going to keep a set of node this and this, or basically I'm going to keep a set of node which are already connected to node 1. For that, I can create a set of int, call it connected, doesn't matter what you call. So how to know which node is connected? So this edge is connected when we were making a BFS call, or we were finding MST of each spanning tree of each connected component separately, and that we were doing in this BFS. So we are adding this edge each time into the new graph. If child is equals to 1, which means we have, if the child is equals to 1, which means we are talking about this edge, right? From this node to this, from this node to this, and so on. So when child is equals to 1, which means we are adding these edges, so which means we are this node is being connected to node 1. So that means current is the node which is being connected to node 1, of course, right? Because child is 1. So in the set that is connected, we would insert this node. So this node is being connected to node 1. I've kept that list to know that which nodes are connected to node 1. Now these many edges we have to add extra. For that we would run a loop is equals to 1, I less than equals to rem I plus plus. Each time we would add an extra edge, or I don't have to actually do this. In the adjacency list of node 1, in the adjacency list of node 1 in the previous graph. So if connected dot find this child, which means if this child is already connected to node 1, sorry, not node, it would be, come on, 1. So if this is already connected, then connected dot find would not be equal to connected dot end. Basically in the set connected, if this child is already there, or basically if from node 1 this is already connected, then connected dot find would not be equal to connected dot end. So if connected dot find child is not equal to connected dot end, that means it is already present there, so we can't add this edge. This edge means child, the edge between child and node 1. And if this is equals to connected dot end, that means this is not connected, this edge is not connected. In that case, what we can do, we can add this edge into the new graph. So into the new graph, node 1 is connected to this child, and in the adjacency list of new graph child, push back node 1. So in the adjacency list of 1 we have added child, in the adjacency list of child we have added node 1, and then remaining minus minus, since we have added one edge. If remaining is double equals to 0, simply break, come out of this loop. So now this should work. So let's test for the second test case. Answer is here. 1 is connected to 2, 1 is connected to 3, 1 is connected to 4. Yeah, as you can see. So let's simply submit it, because the editorial is already too long. So let's see how many errors do I get. Let's submit it. Let me increase. Okay, so it is running on task case 1, on task case 6, 12 dash 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 13. Okay, this is stuck on task case 13 most likely, because we may have, yeah, wrong answer. That is what I was going to say. So I might have done something wrong. So first of all, we have, oh yeah, here visited of node 1, each time we have to mark it as unvisited. The reason, when we made a BFS call from this node, from this connected component, then after adding this edge we made node 1 as visited. So if we are making BFS call from this connected component, this connected component won't be able to add node 1 again if this is visited, and this was marked visited from the previous connected component, so this won't be add this edge. So it is important whenever you are going to, it's not in the new BFS, in this BFS where we are adding MST or a spanning tree of each node. So it is important to mark node 1 as unvisited so that each connected component is able to add this edge, this one. So I think this should do, there should not be any error, and this time we should, so I hope this would pass. Okay, now we are running on test case 11, 18. Yeah, there was the error. Oh come on, don't give me an error on 18 now. Oh, this is painful. Now what? So I've got the error. It is also possible that REM, remaining number of edges, are already 0 when we enter this for loop for the first time. That is why this condition should be here before adding any of the extra edges. So that is why we got the wrong answer. This is the last time, I guess. Again on 18. I think we have got error on test case number 18 again. Oh, finally we got an AC, and it happens many times with myself. So I hope you guys have learned from it. Learn a lot, like not making silly mistakes like me. So this was all about this lecture. I know this was a little longer even for me. So thank you guys for watching, and yep, till the next video drops, keep coding. Thank you.